This is Dr. Hester Yiskout from the University of Lethbridge with the last lecture in the course Glaciology and Glacial Geomorphology. This lecture will be split into two parts, but both are about southern Alberta glacial sediment landform associations. What you see here is the plain above the coulees from Lethbridge, and quite often the landforms around Lethbridge and southern Alberta are quite subdued, so it's quite hard to see from the ground. So sometimes it's better to have an aerial view and use air photos or satellite images. The other thing that you notice from this image is that sometimes the geological outcrops are hard to find on the prairies, which are completely flat. And the coulees are one of the areas where you can actually see the sediment exposed. So I'll actually take you in this lecture past some of the coulee sediments and some of the landforms of Lethbridge. This is a Landsat image of some of the hummocky moraine zone around Lethbridge, just south of the airport. We can actually see this pitted landscape. They're almost like donuts, so there are little hills with dimples on the inside of each of the hills, and they're quite subdued in the landscape. Again, if you drive with a car, they're pretty hard to notice, but from a satellite image like this, you can actually see that this used to be an ice marginal region. So there was the Lethbridge lobe of the Laurentide ice sheet, was stagnant here for quite a while and melted in place. Now, I've told you about hummocky moraines in the last lecture, number 16. So if you want to know more about that, go back to the last lecture. This is a geological timetable, which is a little bit of a fresher wrapper of all the times that we've had of the landscape around Lethbridge building up. And what I want you to know is when you go to the bottom level of the coulees, we only get to the oldest sediment of about Cretaceous age. And then if you go upwards in the coulees, obviously you get into younger sediments. And once you get to the Pleistocene, this is where we've had about eight or nine ice ages, but there's only the last ice age was extended as far as Lethbridge, so we only see till deposits of the last Wisconsin ice age. And then we have some post-glacial deposits that I will talk about in this lecture as well. So here you see some of the Cretaceous deposits that you find if you, for example, take a float in the river on a nice sunny summer day. And what we see is that in the Cretaceous period, which is older than 65 million years, which ended with the extinction of the dinosaurs, we see that the Lethbridge area was a quite deep sea region where muds were deposited in the deeper parts of the ocean, of the inland sea at that time, the Bearpaw Sea, and that was interspersed with shallower conditions or sometimes stormier conditions that were depositing these lighter layers, which are silt or siltstone. Now this material, this shale, which is kind of the darker gray regions, it is still not completely consolidated into bedrock. So if you actually pump a lot of water, like meltwater from ice in this sediment, it will easily deform. And I'll show that later. The glacial tectonites around, in some regions around Lethbridge are really prominent because that pre-glacial sediment was actually really deformable. Now, after that period of time, we actually were out of the deep sea sediments, and they were over the entire prairies. There were big gravel sheets of all the rivers that were streaming off the Rocky Mountains. So the Rocky Mountains were formed between about 85 million and 45 million years ago. And obviously if you have uplift of mountain regions, you also have a lot of sediment production, and in those days we also had a lot of rain. It wasn't the dry area that we now have around Lethbridge. So this entire layer from here to here and extending all the way over there is a layer of between about 2 and 7 meters of gravels, and you really notice it when you actually go on your mountain bike in the coulees. It suddenly gets really steep because it's unconsolidated gravels. Now these gravels have their origin in the Rocky Mountains, so they don't actually contain any crystalline types of rocks. So they're not taken from the Canadian Shield region where we have gneisses and granites and things like that. So after that period, we basically are now into the Pleistocene deposits, and these Pleistocene deposits around Lethbridge, we mostly have till that is pillar-like, as you can actually see over here. There's vertical pillars. This till is very stiff, consolidated, and this was subglacial material under the last extent of the Laurentide ice sheet. When we get out of the ice age, the ice is now retreated far enough. There's some layers over here that may contain proglacial lakes or proglacial rivers. So there's some sands and some lacustrine clays and silts present over there. And then in the last kind of deposits that we see over here, this is a remainder of some sand dunes that were building up. Obviously, if you have an ice sheet, there's still no vegetation in front of it. There's strong katabatic wind, so all the material, the finer material that is exposed in front of these ice sheets can get blown around and build up into dunes, sand dunes. So in this lecture I will talk about most of these different sediments, but sometimes the sediments are actually like forming different types of landforms. So we'll talk about both the sediments and the landforms. So glacial till and glacial fluvial sediments do not contain a lot of organic materials or materials that can be dated with a lot of different methods, and we're mostly relying on paleomagnetism by dating these sediments using magnetostratigraphy. So my colleague René Barendrecht at the University of Lethbridge is a specialist in this, and what you see here is a time scale of most of the Pleistocene period here, where we have colder and warmer periods, and we sometimes have a magnetic field that is normal, as we have right now with kind of the North Pole. If you have a compass needle, the north will actually like point north, and we have periods where that magnetic field is reversed. So every time you see an N or an R, it's normal or reversed, normal, reversed, normal, reversed. Each of these periods we can then actually call a chron. So it's almost like a time clock where we have this period is normal, and then it's reversed, and then it's normal. And what you see, there's some names here, the Brunus chron, the Matuyama chron, that are differentiating. Sometimes within ice ages we have a reversal, sometimes between the ice ages. So if we find a till, you can actually take sediment samples from the till, you orient it, and then you look at the magnetic field that was formed at that time. The tills are much more appropriate to date with this method than a lot of other sediments, because you need to have very fine-grained, like clay type materials that orient to the magnetic field at the time. So that's all I'm going to say about this, but some of these names, Brunas, Matsuyama, Gauss, will actually come back on the next slides. So if you date a till, you may want to know whether it's of the last glaciation or one of the glaciations before. So you take samples of the different levels of the till and you see what the sequence is in the magnetostratigraphy. Here you see the maximum extent of 4 of the ice ages in the last Pleistocene period, with the oldest one in number D and the youngest one in number A. So generally what you can see is during the late Gauss period, this is one of the crons that I talked about in the previous slide, the maximum ice extent was actually larger in the Cordilleran part of the ice sheet than in the Laurentide part, which like hardly has any ice over here. And then with the last periods of the ice ages in the Brunas polarity chron, so now we're like younger than 800,000 years, we then only have an extent of the ice sheets over almost the entire northern part of the North American continent. And what you see also here is that the Cordilleran ice sheet and the Laurentide ice sheet actually coalesced and formed one large ice sheet. So for the Lethbridge region, this actually means that we don't have remains of ice ages mostly before the last ice age extent, and the very last ice age was between about 100,000 years and about 12,000 years from now, and that actually had the maximum extent. That also means that if there were any landforms formed before, in ice ages before, all the landforms would have been destroyed by the erosion or the reworking of the sediments by the last ice sheets. Now we're zooming into southern Alberta and southern Saskatchewan to actually show you the maximum extent of the last ice age, the Wisconsin, where the last glacial maximum was between about 25,000 and 20,000 years ago. Then the ice sheet actually melted back and had a bit of a stillstand and a re-advance in about 14,000 years ago before it really started to deglaciate and melt back to like the little puny ice caps that are still left on, for example, Bylot Island and Devon Island. What you can also see here is the extent of the ice sheets of the ice age before the Wisconsin, so that was, we call that the Illinoisan ice age, where the maximum extent was about 140,000 years. And really notable here is if you think Lethbridge would be approximately over here in each of these maps, the direction of the ice extent and the direction of the ice flow was slightly different between the maximum in the Illinoisan and the maximum in the Wisconsin. So there actually was a lot more ice further west from where this map extent is during the Wisconsin than during the Illinoisan. And basically in Lethbridge we do not have any remains of the Illinoisan ice sheet, so all the tills that we have around Lethbridge are of Wisconsin age. Here we see the sequence of events from the last glacial maximum extent of the last ice age, the Wisconsin, about 25 to 20,000 years ago, to like basically the phase where it was almost completely deglaciated about 6,000 years ago. So from the maximum extent here, you can actually see that Lethbridge was under about 1.5 kilometers or a mile of ice. The ice margin was south from us at about the Milk River Ridge region. We also had a Nunatak, which actually was the Cypress Hills, was a Nunatak at that time. And the Cordilleran ice sheet and the Laurentide tide ice sheet, as you can also see in this image. They coalesced at the maximum ice extent. Once deglaciation starts, what you can actually see is that there's lakes forming on the edge of the ice sheet, and these are very large lakes, and occasionally these lakes actually burst out. And these outburst floods actually formed a lot of the scablands in northern Idaho, for example, part of Washington state, as well as around the southern Alberta region, and including the coulees of Lethbridge. What I explained on the previous slides is a sequence of events of glaciation or deglaciation in the Alberta, southern Alberta to northern Alberta region. And what you have to realize is when you look at geological maps like these, is that you have to put your 4D glasses on. So you have to look at 3D if you want to see proper landforms, but you have to look at a fourth dimension, which is time. Because what you see here is a number of geological deposits and landforms. For example, the morainic landforms that are here in the greenish hues. And they're deposited at different times. So at the maximum ice extent, we actually had a lobe going all the way to the southern Alberta. And the ice was actually around this region. That red region is actually bedrock. That was a nunatak of the Cypress Hills. What we can also see here is this ice thrust moraine. As I said in the last slide, we don't have a lot of that because there wasn't a lot of active ice apart from the maximum ice extent, but you can actually see the ice thrust moraine over here. Now, that was the maximum extent, but we can also see some of the lobes of during the retreat of the ice age. Sometimes there was a little bit of reed fans or a stagnation. So this is one of the lobes. There's the Lethbridge lobe, for example. There's other kind of lobes. If you actually think this is kind of going forward in time, the ice sheet retreats, but like stagnates somewhere. So each of these lobes can actually be several thousand years apart from each other. What we also see here is this yellow hue is the glacial fluvial deposit. So, for example, there are a couple of esker deposits here. There are also like some broader old glacial fluvial river systems. And then we have the bluish areas that are actually like infill everywhere in between the green areas. And during the retreat of the ice sheets, we basically had these ice marginal lakes forming, and they actually filled up the lower areas. For example, here, a lower area on the side of a lobe. So sometimes we now give some of these lakes names like Lake Lethbridge or Lake McLeod. And if we would have been on the field trip, we would have seen some of the deposits of these lake sediments. So what I said in the beginning of this slide in terms of time, obviously if you have a lake deposit, for example here, that lake deposit is a lot younger than the deposit of like all the till material and the hummocky moraine, which is the landform of the till around there. So just kind of realize that. Here we see a map of the bedrock topography on the left, which is the elevation at which the hard rock bedrock is to be found if you actually measure that relative to sea level. So this goes from in the Rocky Mountains from about 1800 to 3600 meters to an elevation of 20 to 300 meters in northern Alberta. On the right side, you see the sediment thickness, and this sediment thickness is basically the quaternary sediments. So these are the tills, the glacial fluvial sediments, the maybe Aeolian sands. So what is really noticeable is that the sediment is a lot thicker in this region. It's several hundred meters thick in this entire zone. And here in southern Alberta is quite evenly in terms of thickness, from a couple of tens of meters to maybe maximum 20-25 meters. So why is the sediment so thick in this northern region? Well, when the ice sheet was actually approaching from the north, so this is the Laurentide ice sheet approaching from the north, okay, it took some sediment with it, so some till was actually smeared out a little bit like toothpaste under the ice, but it encountered these preglacial valleys. And what it did when it actually moved over the preglacial valleys, it first filled up these valleys with all the till and all the other tectonized sediments. And then it actually didn't take much of the sediment with it after it had filled up this this pre-glacial region. So what you can see on the previous slide, which I can't do in this film of this PowerPoint, is that region where we have the maximum thickness are the big pre-glacial valleys in northern Alberta that were actually filled up. So then during the retreat of the ice, what you can see here is a proglacial lake forming, and sometimes there is a bit of a re-advance over here, so the ice is actually further extended in this image than in this image, where we see like the pushing up and the deformation of some of that lake sediment that was deposited during this time.